Welcome to the deep dive. If you've ever felt like staying connected requires a degree in acronyms, think 5G, 10G, DO, CSIS, memo wave, well, you're definitely not alone.
Yeah, it's a lot. The world of internet technology is just moving incredibly fast. It changes how we interact with, well, pretty much everything.
You've shared some great sources looking into this, and they really point to two big things shaping the future, right? There's the evolution of our wired connections, often called 10G, and then this bigger leap in wireless, which is 5G.
Exactly. Two major tracks.
So our mission today is to take those sources, unpack them, and give you the shortcut. We want to figure out what these terms really mean, get past the marketing buzzwords.
Understand the tech behind them.
Yeah, see how they fit together because, spoiler, they're not really enemies.
Not really, no. But more like partners, in a way.
And look at who's actually building all this, and maybe the big one. Talk about the eye-watering cost of making it happen.
It's significant. But hopefully by the end of this deep dive, you'll have a much clearer picture of tomorrow's connectivity backbone.
Okay, let's unpack this, and maybe start with 10G. When you hear 10G internet, what are we actually talking about? Is it just 10 times faster internet?
Well, the 10G does signal the speed goal, aiming for 10 gigabits per second. Symmetrical, ideally.
Okay.
But it's less a single product you buy right now and more like a roadmap, a platform. It's being driven mainly by the cable industry, think cable labs.
Okay.
And it's really about the next generation of wired broadband, evolving the networks, the cables, already running into most homes and businesses.
So we're talking about the coaxial cable, the fiber optic lines, that kind of infrastructure.
Precisely. It's mainly focused on upgrading the existing hybrid fiber coaxial networks, HFC, the standard cable internet lines.
Right.
But the 10G platform, as they call it, also covers improvements for pure fiber-to-the-home FTTH setups. But that key goal is symmetrical 10GBPs.
Symmetrical, meaning upload and download speeds are the same. Because, man, right now my upload often feels like it's, stuck in the past compared to downloads.
That's exactly the pain point 10G wants to fix on the wired side. And the technical wizardry to get there, especially over existing cable lines, mostly comes down to DLCSS 4.0.
So it says 4.0. I've seen that pop up. What's the big deal with this version? What makes it different?
Two really big innovations. First is full duplex DOCSIs, or FDX. This is genuinely clever stuff.
Okay.
Traditionally, uploads and downloads on a coax cable needed separate frequency lanes, separate spectrum. FDX lets them use the same chunk of spectrum at the same time.
Wait, how does that even work without interference?
It involves some pretty complex signal processing, like super advanced echo cancellation. Imagine two people talking loudly at the same time in a room, but each has perfect noise-canceling headphones tuned only to the other person.
Huh. Okay, that's a neat trick.
It is, and it dramatically increases the upstream capacity, the upload speed, without needing completely new frequencies, which has always been the bottleneck for symmetry on cable.
That is fascinating. So FDX fixes the upload problem. What's the other part of DOCSS 4.0?
That's Extended Spectrum DOCSS, or ESD. This one's maybe a bit more straightforward. It basically just expands the range of frequencies used on the coaxial cable itself.
Like adding more lanes to the highway.
Exactly. Pushing the upper limit from around 1.2 gigahertz in DOCSS has 3.1 up to 1.8 gigahertz. More frequency range equals more total bandwidth, more capacity for data.
So DOCSIS 4.0 uses both FDX and ESD together. And that's the path to symmetrical 10 GBPs over existing cable lines. That sounds huge, using mostly wires that are already there.
That's the main advantage for the HFC networks, yeah. Leveraging the existing physical plant is key. But like we said, 10G isn't just about cable.
Right, it also includes fiber upgrades for areas that already have fiber to the home.
Correct. For those pure fiber networks, 10G involves moving to faster optical standards within what's called a passive optical network, or PON.
PON, okay.
The main standard being deployed now is XGS-PON. That's an international standard delivering symmetrical 10 GBPs over fiber.
Symmetrical 10 gigs over fiber. Got it.
And there's even NG-PON2 on the horizon, which could offer even higher speeds, like 40 GBP shared, providing a path for future growth.
And presumably the whole network, the core, needs to get smarter to handle all this speed, not just the lines to the house.
Oh, absolutely. The 10G roadmap isn't just about raw speed. It includes things like edge computing, bringing processing power closer to the user.
For lower latency.
Exactly. And using things like software-defined networking, SDN, and network function virtualization, NFV, to make the network more agile, more efficient, more responsive.
So if we zoom out, Beyond just the 10 GBPs number, what are the main benefits 10G aims to deliver?
Well, the symmetrical speed is huge for cloud applications. Big uploads, high-res video calls, remote work with large files.
Right.
Then there's low latency they're targeting under 10 milliseconds typically.
Which is great for gaming, real-time stuff.
Definitely. Plus enhanced security features and the inherent reliability you get with a wired connection. It's generally more stable, less affected by, say, bad weather than wireless.
Makes sense.
And ultimately, it's about future-proofing. Providing the capacity for whatever's next, immersive AR/VR, holographic chats, you name it, the data needs of smart cities.
Okay, that gives a really solid picture of the wired evolution. Now, let's completely switch gears. Let's talk 5G. Most people know it from their phones, right? But the sources suggest it's way bigger than just faster mobile speeds.
Oh, absolutely. 5G, the fifth gen of cellular, it's a different beast altogether. Speed is definitely part of it. Multi-gigabit peaks are possible.
Wow.
But it's fundamentally designed to enable a whole new ecosystem of connected things. Devices, services, applications we couldn't really support before. It's also about ultra-low latency, massive capacity for devices, and better, more consistent availability.
So how does 5G manage that leap compared to 4G? It can't just be bigger antennas, right?
Not at all. It's built on completely new radio tech, 5G new radio, or NR, and a totally redesigned core network. A huge part of it is flexibility with radio frequencies with spectrum.
Okay, spectrum. Explain the different bands people talk about, low, mid, high band, or mmWave wave. Why does it matter?
Think of them like different tools for different jobs. Low-band spectrum, that's frequencies below 1 gigahertz.
Okay.
It travels really far, penetrates buildings well, great for wide area coverage, but the speeds are lower, maybe hundreds of Mbps. It ensures you have a connection in most places.
Right, the coverage layer.
Exactly. Then you have mid-band, generally 1 to 6 gigahertz. This is often called the sweet spot or the workhorse.
Why is that?
It offers a really good balance between coverage and capacity. You get decent range and good speeds, hundreds of Mbps, sometimes low GBPs. A lot of the initial 5G deployments you see are focused here.
Okay, makes sense. And then the really fast stuff, the millimeter wave, that's the one needing tons of small antennas.
That's high band, or millimeter wave, yeah. Frequencies typically 24 gigahertz and up. This is where you get those crazy multi-gigabit per second peak speeds and massive capacity.
But the catch is...
The catch is range. It travels very short distances, like maybe a city block or less, and it really doesn't like obstacles. Walls, windows, even leaves on trees can block it.
Wow, so it's for very specific spots.
Dense urban areas, stadiums, convention centers, airports, places where you need huge capacity in a small footprint.
Okay, so 5G uses all these different spectrum types. How does the tech actually handle connecting so many devices, especially efficiently?
The key technology there is massive MIMO. That stands for multiple input, multiple output.
WIMO, right.
Base stations use a lot of antennas, like 64 transmit and 64 receive, or even more, to talk to many users simultaneously using multiple data streams. Think of it like having dozens of focused beams instead of one big floodlight. Increases capacity and efficiency hugely.
And beamforming, is that related?
Yeah, beamforming works hand in hand with massive MIMO. It's the technology that precisely steers those radio signals directly towards individual users or devices.
Like a spotlight following you.
Kind of, yeah. Instead of broadcasting everywhere, it focuses the energy where it's needed. This is absolutely crucial for making mmWave usable to overcome its range and signal weakness issues.
And because mmWave is so short range, you need a lot more of those spotlights, those base stations.
Exactly. Yeah. That's why you hear about the need for dense networks of small cells, smaller, lower power base stations mounted on things like lampposts, traffic lights, building sides. You need a lot of them close together for millimeter wave coverage.
This is sounding incredibly complex to orchestrate. How does the network adapt to all the different things connecting to it? You know, a phone needs something different than a self-driving car or a factory sensor.
That's where a really powerful concept called network slicing comes in.
Slicing.
Yeah. It lets operators essentially carve up their single physical 5G network into multiple virtual networks. Each slice could be customized for very specific needs.
Like what?
Like one slice might guarantee ultra-low latency for industrial robots. Another slice might be optimized purely for high bandwidth, maybe for video streaming. A third slice could be designed for connecting millions of tiny, low-power IoT sensors that only send data occasionally.
Wow, okay. That's really flexible. And you mentioned edge computing earlier for 10G. Does 5G use that too? Mobile edge computing? MEC.
Absolutely, and it's arguably even more critical for 5G. MEC puts computing and processing power much closer to the user, right out at the edge of the network near the cell tower.
Why is that so important for mobile?
Latency again. For real-time applications like cloud gaming, augmented reality, or vehicle-to-everything communication, sending data all the way back to a central data center and getting a response takes too long. MEC drastically cuts that round-trip time.
Makes things feel instant.
That's the goal. We also hear about standalone versus non-standalone 5G, NSA versus SA. What's the difference there quickly?
Good question. Early 5G often used non-standalone, or NSA. That meant using the new 5G radio transmitters, but still relying on the existing 4G network core for signaling and management.
Okay, kind of leaning on the old system.
Right. Standalone, or SA, means using both the new 5G radio and a brand new cloud-native 5G core network. It's the SA architecture that really unlocks the full potential, the super low latency, the dynamic network slicing, all the advanced features. It's the true endgame for 5G.
Got it. So, summing up 5G's big benefits.
You've got the potential for much higher mobile speeds, especially with M-Wave. You have ultra-low latency capabilities, targeting less than a millisecond for critical uses.
Huge connection density, supporting potentially millions of devices per square kilometer, essential for the Internet of Things.
High mobility, obviously. Seamless handovers, that network slicing flexibility we talked about.
And it enables fixed wireless access, FWA, using cellular to provide home or business broadband, competing directly with wired sometimes.
Okay, so we have 10G, pushing the wired boundaries for speed and reliability, and 5G, this wireless transformation focused on mobility, latency, and connecting everything. The sources you shared were really clear. These aren't really competitors fighting for the same turf.
That's probably the single most important takeaway. They are largely complementary. They serve different primary needs using fundamentally different infrastructure.
Right. 10G is all about that fixed wired connection, the pipe coming into your home or office. Super reliable, super high capacity.
While 5G is primarily about mobile access to your phone, your connected car, and that fixed wireless access option, bringing broadband over the air.
So the use cases diverge quite a bit. 10G for the heavy lifting at a fixed location, 5G for mobility, for IoT, for specialized things like autonomous vehicles, private networks for factories, and FWA.
Exactly. One uses physical cables, fiber, coax. The other uses radio waves.
And the speeds. Both talk about 10 Gbps, but it sounds different in practice.
Yeah, 10G aims for symmetrical 10 Gbps delivered reliably over that wire. 5G can hit peaks of 10 Gbps or more within a M-wave under ideal conditions, but your typical experience, especially on mid-band, is more likely hundreds of Mbps to maybe a gigabit or two, and it can vary more.
What about latency?
Both aim low. 10G offers consistently very low latency, typically under 10 meters today. 5G targets sub-1 meters for specific ultra-reliable, low-latency communications, or URLLC.
That's a mouthful.
It is.
Yeah.
But typical 5G latency right now is often more the 10-20 meters range. Still very good, but maybe not quite as consistently low as a dedicated fiber line for general use yet.
And reliability. Wired versus wireless.
Generally, wired 10G is seen as more consistently reliable, less prone to interference, weather issues, congestion in the airwaves. 5G is getting very reliable, but it can still be affected by distance from the tower, buildings, heavy user load, even sometimes rain, especially for millimeter wave.
Makes sense. And the infrastructure build-out looks totally different, too.
Completely. 10G means upgrading cable plants to DAO CSIS 4.0, maybe pulling new fiber, which is expensive digging and construction. 5G means deploying potentially millions of small cells, getting site permits, running power, crucially, running high-capacity fiber backhaul to all those cell sites, plus building a whole new 5G core network. Very different challenges.
It really sounds like a monumental effort to bring either of these to scale. It involves so many different companies and organizations around the world. Who gets the credit, or maybe who are the key players driving this?
It's genuinely a huge global collaboration. For 10G, specifically the cable side, Cable Labs is a major force. They're the R&D consortium for the cable industry, driving the 10G platform idea and the DTO CSA standards like 4.0.
Okay, Cable Labs for cable tech. What about the underlying standards?
Foundational work comes from groups like the IE for things like Ethernet, and the ITUT develops the international standards for optical networks, like XGS-PON used in fiber 10G.
And then the company's actually building it.
You have the service providers, Comcast, Charter, Cox on the cable side, AT&T, Verizon, Google Fiber on the fiber side investing billions to upgrade or build networks, and the companies making the gear. Broadcom, Intel making chips, Nokia, CommScope, Cisco making network equipment.
Right. And for 5G, who's behind that wireless revolution?
The main global standards body is 3GPP. That's a huge collaboration defining the technical specs for 5G NR and the core network. The ITUR also set the high-level performance targets, what they called IMT 2020.
And the big names we recognize.
The mobile operators, obviously Verizon, AT&T, T-Mobile in the US, China Mobile, Vodafone, Orange globally, they define requirements, test, deploy. Then the big network equipment vendors, Ericsson, Nokia, Huawei, Samsung, ZTE, they build the base stations and core systems.
Can't forget the phones themselves.
Exactly. Chipset makers like Qualcomm are crucial. And device manufacturers like Apple, Samsung, Google making the 5G phones, tablets, routers, plus, decades of underlying research from universities and labs worldwide made the foundational tech possible.
It's quite an ecosystem. Just thinking about the scale is humbling. And all that work, all that R&D, all that infrastructure, it must cost an absolute fortune. What's the financial reality here?
Staggering is probably the right word. For both 10G and 5G, we're looking at multi-billion-dollar investments just within individual countries, potentially trillions globally, over the deployment lifecycle.
Okay, break it down. Let's start with the cost of 10G.
Even though 10G often leverages existing wires, the infrastructure upgrade is still incredibly expensive. For cable networks moving to dial CSS 4.0, that means replacing equipment in the headends, installing new optical nodes deeper in the network, maybe even replacing amplifiers or parts of the coax cable plant itself. It's a multi-billion-dollar effort for each major operator.
And for fiber, even if fiber is already there.
If they're building new fiber to the home, that's one of the most capital-intensive things you could do. Trenching streets, permits, labor, it's huge. Even upgrading existing fiber networks to XGS-PON requires new optical line terminals, OLTs, in the central office, and new optical network terminals, ONTs, at the customer premise. Still significant cost.
So that's the cost to build the network. What about for you, the end user?
Well, you'll probably need new equipment, a DOS ESC 4.0 modem, or a new fiber on Trouter. That might be a purchase or a lease fee. And the subscription plans for those top 10 Gbp speeds. They'll likely start as premium, higher-priced tiers. Over time, competition should hopefully bring prices down, but initially, expect to pay more.
And maybe even needing to upgrade my home Wi-Fi router to handle that speed.
Potentially, yes. To get the full benefit inside your house, you might need a newer router, and maybe even check your Ethernet wiring if you use wired connections.
What about businesses? Is the cost justified for them?
Often, yes. For businesses relying heavily on cloud services, large data transfers, video conferencing, that symmetrical, reliable high capacity of 10G can directly translate to productivity gains, making the premium cost easier to justify.
Okay. Now, 5G costs, you said extremely high earlier.
Yeah, the scale is immense. Especially for the M&Wave flavor of 5G, operators need to deploy an incredibly dense network of small cells.
Right. Thousands, millions, maybe?
Potentially. Each one needs a site lease or permit, power installation, and crucially, high-capacity fiber backhaul connecting it back to the network core.
So they're basically building a massive fiber network just to support the wireless one.
In many areas, yes. That fiber backhaul is a huge, often overlooked cost component of 5G. On top of that, they're replacing or upgrading existing 4G radio gear, building out that entirely new cloud-based 5G core.
And buying the spectrum.
Operators spend billions, sometimes tens of billions, just for the licenses to use the radio frequencies in government auctions before they even build anything.
Wow. So what does this mean for the consumer's wallet with 5G?
Well, you need a 5G device. Initially, phones and routers were pricier, but costs are definitely coming down.
Okay.
Data plans might be tiered, or unlimited plans might cost more for premium 5G access. But the fixed wireless access, FWA offerings, are often priced very competitively against traditional wired broadband. That's a key strategy for them.
And for businesses thinking about 5G?
Some large enterprises might invest in their own private 5G networks for factories or campuses, which is a big upfront cost. But the flip side is that 5G enables new revenue streams and efficiencies. Think IoT data, remote machine control, new customer experiences via AR that could provide a return on that investment. So, yeah, the bottom line on cost, both 10G and 5G require absolutely massive, multi-billion-dollar investments across the board. Initial costs for the very top tiers of the latest equipment might be higher for consumers, but the long-term vision is to create these ubiquitous, super fast, low-latency networks that unlock completely new capabilities and economic value, providing significant value, hopefully, despite the huge initial outlay.
So we've taken this deep dive, and I think the picture is much clearer now. 10G and 5G.
Yeah.
They're not really fighting, they're parallel tracks, right? 10G is evolving that reliable, high-capacity wired connection we depend on at home and work.
And 5G is pushing the envelope on wireless speed, sure,
Hmm.
but also massive connectivity, mobility, ultra-low latency, enabling things we couldn't do before, untethered.
Understanding the tech, like DO CSIS 4.0 or network slicing, knowing who's involved globally and grasping the sheer scale of the investment involved, it really helps frame where connectivity is heading.
Definitely. You hopefully have a better sense now of what symmetrical 10 GBPs over cable or fiber really means, why 5G needs different spectrum bands, and yeah, why building either of these costs billions.
Okay, here's where it gets really interesting for me and maybe raises a question for you listening. As these technologies, this incredible speed, this near instantaneous response, this ability to connect almost anything as they become more common,
Hmm.
how might that fundamentally change things beyond just, a faster Netflix? Could it reshape how we think about remote work or education or healthcare with things like remote surgery? Or even how we interact with our cities through augmented reality or autonomous systems?
That's the big question, isn't it? What happens when the network is no longer the bottleneck for imagination? Something to think about.